This question is related to the setup for the strong law of large numbers. And we are given a sequence of independent identically distributed random variables xi with probability density function fx, which is 1 over pi, 1 over 1 plus x squared for x and r. So this is a Cauchy density function. We also define zi to be xi times the indicator that the magnitude of xi is less than or equal to I. And we are asked to find what is the probability that xi differs for zi infinitely often. Well, they would differ when the magnitude of xi is greater than I. Now, we know from the setup of the strong law of large numbers, in particular lemma truncation, that this probability that they differ infinitely often is 0 when x1 or xi has first moment, meaning that the expected value of the absolute value of x1 is less than infinity. To solve this problem, we first note that the expected value of the absolute value of x1 is equal to the integral of 1 over pi times 1 over 1 plus x squared from minus infinity to infinity. And that can be divided into an integral from minus infinity to 0 of 1 over pi times minus x over 1 plus x squared, plus the integral from 0 to infinity of x over 1 plus x squared times 1 over pi. Now these are both equal, and so we could just evaluate 2 over pi times the integral from 0 to infinity of x over 1 plus x squared. And this is equal to 1 over pi times the limit as capital T goes to infinity of ln 1 plus capital T squared, and that's equal to infinity. This integral is equal to that expression since the antiderivative of 2x over 1 plus x squared is equal to ln 1 plus x squared. And so this first gives us a hint that we might have a different answer, in that the expected value does not exist, meaning the expected value of the absolute value of x1 is infinite, and the lemma that we use, this truncation lemma, does not imply. So we cannot assume that this is equal to 0. Indeed, with some anticipation of use of Borel-Cantelli, we can look at the sum of these events. So the sum I equals 1 to infinity of the probability that xi is not equal to zi. Well, as we mentioned before, by the definition of zi, these events, or they're the same event as the magnitude of xi is greater than I. So this sum is just the sum I equals 1 to infinity of the probability that the magnitude of xi is greater than I. But xi has the same distribution as x1. And so by the identical distributions, this is the sum I equals 1 to infinity of the probability that x1 is greater than I. And this starts to look like our alternative expression for expectation. And indeed, since the probability that the absolute value of x1 being greater than t is less than or equal to the probability that the absolute value of x1 being greater than I, when t is between I and I plus 1, we have that sum is greater than or equal to the integral from 1 to infinity of the probability that the absolute value of x1 is greater than t dt. This is just by the decreasing nature and integral approximation. Now, this integral from 1 to infinity is the same as the integral from 0 to infinity minus the integral from 0 to 1 by linearity. And the integral from 0 to infinity of the probability absolute value of x1 being greater than t dt is just the expected value of the absolute value of x1. On the other hand, the integral from 0 to 1 of any probability is less than or equal to 1. And so we know that this line is greater than or equal to the expected value of the absolute value of x1 minus 1. But from our first calculation, we computed that the expected value of the absolute value of x1 is infinity, so this is infinity. So the sum I equals 1 to infinity of the probability that xi is not equal to zi is infinite. Now these events, xi not equal to zi, I equals 1 to infinity, are independent. And so Borel-Cantelli too applies, and it tells us that the probability that xi is not equal to zi infinitely often is 1, meaning that our method of using the truncation lemma in the law of large numbers would not apply.